So now let's talk about the same set of operations which we discussed at the time when we discussed about adjacency matrix. So these are the same set of operations which we will discuss today. If we are given a task to find all the edges of the matrix, what will we do? So the program which we will write has to go and scan this whole entire array, and then for every index it has to go inside this list, and it has to scan the entire list and get all the neighbors and then form the edges and return the set of edges or list of edges, whatever, right? So that is what we need to do if we need to find all the edges of the graph. So this is pretty straightforward. So what do you think? What is the time complexity it will be for this operation? So if you think about it, this array size is equal to the number of nodes in this graph, and this list of neighbors is basically equal to the degree of that particular vertex. So on an average, if we talk about the time complexity, then it should be the asymptotic time complexity should be O of n, and for every vertex we have to traverse the list of size degree of that particular vertex. So it is n into degree of vertex. Right? Okay. So another operation, find all the neighbors of the vertex. So if we are given the vertex number 1, and if we want to find out all the neighbors of that particular vertex, then simply we have to visit index 1, location of index 1, and just traverse this whole list. So visiting the index 1 will be a constant time operation, and then further we have to traverse this list. So that will be the degree of that particular vertex. So the asymptotic time complexity will be degree of vertex. The third operation is if we want to check if the direct edge exists between two nodes. If the nodes which are given in the input are 2 and 4, so what we have to do is, either we have to, as this is a directional graph, we can either go to index 2 or index 4 and then search for other vertex. So for an example, if we visit index 2, then we have to scan the whole array, and we have to check if we find vertex number 4. So this operation is again O of degree of vertex. So these are the time complexities of this particular graph representation. And what about the space complexity? How much space which we might need to store this representation? So the space required to store this entire graph in terms of adjacency list, it is order of n into degree of vertices. So if you compare the space complexity, it's a little better than what we um, saw um, uh, when we saw the space complexity of the adjacency matrix. Um, and even if we compare the operations, when we perform those operations, like this operation in adjacency matrix, it took its time complexity was n square, but here it is little better. It is n into degree of the vertex. Even for this operation, to find the neighbors of the vertex, the time complexity was n. But here it is degree of the vertex, because we are not storing entire, we don't have to scan entire what you say, entire the list, the list size on an average, the list size in every index will be smaller than the number of vertex, right? Because we are considering, assumption is this graph is not a dense graph, it's a sparse graph. So it will be definitely lesser than n. And here, if you see here in this third operation, adjacency matrix is doing way better than in this adjacency list. So this operation was constant time operation for adjacency matrix, but for adjacency list, this operation is degree of the vertex. So we will see another variant of adjacency list in next video, and that is, as I said, it is a variant of adjacency list, and that particular representation will basically overcome the weakness of adjacency list in terms of this operation, and we can achieve, we can do this operation with the constant time complexity. So let's talk about the program, because just to keep the video shorter, I have already created this program. I have already coded this. So I will just run you guys through the program. So this is the class adjacency list graph, and this method, get adjacency list. The input parameters are age list, which is the original input which we will feed to this method, and the total number of vertices present in that graph. And the return parameter is the list, adjacency list. So that is basically the list of integers. So initially, what I'm doing is I'm creating an adjacency list, and then I'm initializing the adjacency list. I'm creating the blank list of integers inside the list. So I'm doing it for 6 times, because we have the vertices from 0 to 5. So there are total 6 vertices. So we need 6 lists. And then this is the logic where this is pretty simple and straightforward logic, where we are basically scanning through the age list, and then we are figuring out who is the neighbor of who, and placing those node numbers accordingly. So because this is unidirectional graph, for both the nodes, we have to mark them the neighbors of each other. So node 0, we are here for node 0, we are marking that 1 is the neighbor of node 0, and the node at the location 0, and in this line we are marking the node at location 1 in that edge list uh, as the neighbor of node 0. So because it is undirected graph, we have to do it both way. So um, we are after this we are just returning the list, and here basically we are preparing the input. You might have seen it is the same input which we have seen here, and using that input I'm just creating the input, creating the edge list, and then passing it to this method, and then calling this method. So if you run this program, it looks something like this. So it is similar to what we have seen. Um, so you can, as I said, I will keep the link in the description, and you can just play with this program. And if you want, you can add some operations and do whatever you need to do. So that is all for this video. And another important thing which I wanted to point out is if we have the nodes with the convenient integers as their numbers, then this is most suitable structure. But if we have the nodes with some names, like names of the cities or names of the states, then probably you cannot directly use this kind of structure, right? So as I said, in the next video I will be talking about the variant of this adjacency list representation, and that this data structure will even take care of this thing, and you will be able to use um, integers or string or whatever. You can name the nodes in any way possible, and you can use that representation to represent your graph. So for this video, that is all I have. See you in the next video. Bye bye.